good audience here. So we can start now, Tapasvi. So I would like to thank you everyone to join this webinar. So this webinar is, as its name is, processing AI meets microwave spectroscopy. Mm, Yes, and which will be help us to understand about the hidden properties of matter through microwaves. So our speaker is Tapas Chakravarti ji. Can you just please go ahead to the next slide?
Yeah, just a minute.
So before starting our webinar, I just requesting you all of you to mute your cell phones, or if you can just switch off, that would be good. After that, in the end of the session, we have a Q&A. And if in case you have any of the questions which will be unanswered in this session, you can just mail us at contact@saracasolutions.com, or if in case you need any support from our side, so that will be a good platform to reach out to us. Can you just go next slide, sir? Okay. So this is nice picture, sir. It's really a good one. So please meet our speaker. So Chakrabarti ji having a good experience in RF and microwave engineering. He is having around 40 years of experience with wireless communication, embedded system, advanced sensing technology, and product innovation. So today we have a chance to use his experience and build our knowledge in this area. So he's currently serving as our principal scientific advisor at Saraca Solutions, with guiding innovation in microwave sensing, healthcare technologies, and for the IoT engineering system with the intelligent part. So that's a good knowledge session for us to understand about the microwave and the spectroscopy part. And he's having a significant contribution to the antenna design, RFID systems, microwave imaging, and biomedical sensing part. So today we will use his skills to understand what the spectroscopy and what the microwave part. Apart from this, he is having a senior member of IEEE, that's Dr. Chakravarti has authored numerous technical publications and holds multiple patents in wireless communication and sensing technologies. So I would like to thank Tapasri to find out some time to give us a knowledge session and the webinar on this topic. Over to you, sir. Now you
Thank
can.
you. Thank you, Umesh ji. And so, good evening, good morning, depending on where in the world you are joining from. So, thank you for joining today's session. Now, every material around us holds some secrets in how they respond to microwaves. And in today's session, we will outline the methods for reading those secrets and also see how AI is transforming this field of microwave dielectric spectroscopy and thereby dielectric material characterization. Now, today's agenda is broadly divided into three. It has three broader scopes. We will begin with the why part, why it is important. Now, material quality assessment is important more than ever. Getting it wrong is very costly, and the methods that we have relied on are reaching their limits. From there, we will move on to see what is microwave dielectric spectroscopy and try to understand the key aspects of dielectric property measurement with some case studies. And finally, we will come to the how part. We will get practical, we will discuss the challenges that are prevalent in this field and how AI can possibly answer these challenges of FDS, what are the current frontiers through 2026, and then we will close with Q&A. Now, at the heart of modern technology and medicine lies a single class of materials, which is dielectric. So, what exactly is a dielectric? Simply put, It is an insulator, a material which does not carry current, but it responds to the electric fields. Its charges shift, it stores and releases energy, and this subtle response is the material's fingerprint, exactly what microwave spectroscopy is meant to read. Does it matter? Yes, it matters a lot. We are full of dielectric around us. All these devices we use, every smartphone, satellite, medicine, even living tissue consists of dielectrics. So trillions of dollars rest on this getting this correct. So it makes the measurement of these materials accurately and fast a very high stakes problem. Let us also appreciate that the material's quality hides in the details. Things like moisture, composition, structure, and unseen defects all shape how a material behaves. But irrespective of such, every material shows a measurable signature. And the best part of electromagnetic method is that through electromagnetic method, we can read this response fast with no contact and certainly no damage. So where does this demand come from? Three forces. The first force is this connected world demands. We are moving into 5G, 6G, and higher frequencies, millimeter wave and sub-terahertz. So RF and antenna materials are to be qualified for design and manufacturability. The second part is industrial IoT and smart manufacturing, things like inline quality control like food, pharma, electronics, etc. And the third aspect is non-invasive diagnostics. Now, microwave sensing is radiation free, so it is not hazardous to humans. And there are a lot of works that uses this kind of microspectroscopy for diabetes and cancer screening. Now, the common thread across all is that the demand for fast, precise, non-contact material measurement, exactly what MDS delivers. Let us now look into some strategic applications of microwave spectroscopy. You see the right hand side picture. In the right hand side picture, I have broadly categorized the different applications in two categories. One is the industrial applications, the second one is biomedical applications. Under this industrial application, there are applications like food industry, moisture content, quality control, shelf life, particularly for perishable goods. Second part is agriculture. Very important area is soil moisture analysis, grain quality. They are used in precision farming. In material science, where it is very normal, but one of the most important emerging area is composite material testing to see whether there are hidden defects in composite materials or not. And there is also an emerging area in pharmaceuticals. Apart from its ability to see formulation analysis, we can also try to see whether the spectroscopy helps in understanding whether the quality of these medicines or tablets have degraded when they are in flight and at the last point of sale. On the other side, there is biomedical applications, cancer detections. It is a non-invasive screening, tissue differentiation, continuous glucose monitoring. Then tissue characterization. Areas that are being investigated are burns, wounds, etc. And biosensors are very important area, lab on a chip kind of uh, devices. Now, considering all of them, you see across all these applications, there is a common theme that we take this material property and convert this into actionable data, and that what makes microwave dielectric spectroscopy important. Now, with this, why that is being clear, now we come to what is microwave dielectric spectroscopy. So, microwave dielectric spectroscopy probes how a material responds to these microwave frequency electric fields. So all dielectrics are characterized by a property that is called complex permittivity. Here it is written epsilon is equal to epsilon prime minus j epsilon double prime, where the second part, j epsilon double prime, is imaginary number. Now, epsilon prime is essentially the energy stored by the material, and epsilon double prime is the energy lost as a heat. But how do we measure its properties? To see this, we look at the schematic on the right hand side. At the center of the schematic, there is a dielectric material block. Let's assume that it has these molecules have a dipolar, water-like dipolar elements which rotate to align themselves with the incoming electric field. Now, on the left-hand side, we assume there is a microwave source which can be swept from very low frequencies, say 1 gigahertz, to high frequencies. Now, at every frequency, there is a signal, there is a wave that is falling on this dielectric material. Some part of it gets absorbed inside this dielectric material. A large part of it gets transmitted, and a part of it also gets reflected due to the differences in permittivity between air and the material at the interface. Now we capture this reflected wave and the transmitted wave, that is transmission coefficient and reflection coefficient, through using a very high precision instrument called vector network analyzer, and from there we plot the frequency response of the signal. Essentially what it means that on the x-axis there will be frequencies, and the y-axis will be the amplitude of the transmission coefficient or reflection coefficient. But we will see that there will be a particular frequency for every dielectric for which we will see a dip, a null, where a resonant property is observed, and that is essentially the fingerprint of that particular material. This fingerprint reveals the composition, water content, phase changes, everything. So the key takeaway is every material carries a microwave fingerprint. Now MDS reads it to reveal composition and condition without ever touching that sample. So this is an important aspect of it. So coming back to the permittivity spectrum, now we are calling it as a material signature. So the permittivity, if we sweep from very low frequency to ultra-wide frequency, consider any hypothetical material, it shows a series of phenomena, and that essentially defines that material. Let us say we start at a very low frequency kilohertz range and move up in frequency. We see a high value of permittivity, and the phenomena that takes place is all about polarization, and the polarization effect here is space charge. Space charge is a very unique phenomenon which happens due to the free carriers at the interface of two materials, and it is unique in the sense that an estimated dielectric permittivity or relative dielectric constant due to this method is usually much higher than the intrinsic bulk property of the material. Now, what happens as we push the input frequency higher and higher? Let us say we have come to the megahertz region. Now, this space charge polarization drops off, and there is a step down in permittivity. We come to the dipole region, where the molecules which have permanent dipole like water, they rotate to align themselves with input electric field. That is the polarization. Now, why it happens? It happens due to a phenomenon called relaxation. So, when polarization is a method of rotation inside the molecule, when the electric field comes, the electric field is also oscillating, but at a certain frequency, the exciting oscillations are much higher, much speedier as compared to the response. So that particular response drops off. So at microwave range, we are talking about dipolar, and which then at a higher frequency it moves into ionic. For example, elements like NaCl, where the ions get displaced, and at optical and ultraviolet range, where the electron crowd shifts with respect to the positive nucleus. Now, uh, irrespective of the entire frequency band, which is for our understanding, because we are talking about MDS, the richest band for biological and moisture sensitive matter is this dipole region, this dipole effect. And if you see all these peaks over here in epsilon double prime, these peaks are compositional fingerprints. Their position and height reveal what a material is made of. Now, two numbers define a dielectric material. We have discussed about that, but we can actually discuss it again. So the numbers are, one is permittivity for epsilon prime, the dielectric constant, which is kind of energy storage, how strongly a material stores electrical energy in a field relative to vacuum. And this is very key for capacitors, substrates, and antenna design. And the second part is loss, epsilon double prime, where the energy that comes to the dielectric material, this is non-usable, it gets lost as a heat as lagging dipoles rub against the alternating fields. Now remember that no material is lossless. High epsilon double prime means strong heating. Now on the right hand side, I have put a representational table covering some typical materials and measured at my 2.45 gigahertz. Please remember that air is the reference. So it has a relative dielectric constant. Here I have put it is a permittivity, but essentially it is epsilon r. It has 1 and it is lossless, so it is 0. So all natural materials, whether it is Teflon, silica, alumina, up to water, which is very high, all higher than epsilon, and all of them show some amount of losses. The question is, why microwave frequencies are the right tool? We have already discussed it briefly. We said that it is the richest frequency band for biological samples. Now, microwave works for two kinds of material. The first one is the water-bearing ones, things like food, tissue, soil, which is affected by different moisture contents, and these moisture contents are relatively easy to read. But irrespective of that, microwaves can also work for even bone dry materials like ceramics and polymers, which have their permittivity set by their structure, the density, and their composition. Now, the important aspect of microwave is this: for this kind of materials, microwave can penetrate through the entire volume. Since it can penetrate through the entire volume, then there are hidden voids. Then let's say there are lumps formed inside the material due to change in density. Due to some effect, there is a localized phase change. Microwave sees those and all of them lead to the measurable signatures. On the right hand side, there are some key frequency landmarks. From 0.3 to 3 gigahertz, typically they are even used as ground penetrating radars, but from the perspective of spectroscopy, we say that this is the frequency which works best for deep tissue hydration and thick materials. 1 to 10 gigahertz is heavily researched because it is a sweet spot. It has the ability to penetrate, yet it gives a reasonable final spatial resolution. So it is used for compact biosensors and lab on chip devices. If you are looking for detecting very low level of moistures, then let go for 18 to 20 gigahertz because water responds most strongly. And the higher frequencies, millimeter wave terahertz, are getting nowadays getting investigated for very thin, very high resolution and things like skin imaging. So now we have seen that what exactly constitutes the dielectric property and what are we going to measure. Next, we come to the point as that how do we measure this permittivity? So measuring how a material perturbs a microwave signal is essentially realized through three complementary instrument families. So the first one is called a broadband non-resonant type of measurement. So we have said that when a microwave source falls on the dielectric material, some part of it is transmitted, some part of it is reflected, and we take the signal to a precision instrument like a VNA, vector network analyzer. So the VNA has probes attached to it, and these probes are broadband. That means we can sweep the source from very low frequency to high frequency and then capture the signal that is coming out after interaction with these dielectric materials. We capture this response across the entire frequency band. It gives us a very wide eye view of the property, how it behaves over a wide frequency range. Because we are using a very wide frequency range, these are not very highly sensitive, but it gives you a broad spectrum analysis of how the material behaves. The second one is resonant. These are small printed circuits, very compact in nature, but essentially these are part of the design. Design is a very specialized job. This leads to very high sensitivity at a single frequency. Why it happens is that through conscious design, we enhance the localization of electric field at a certain point on which we put our analyte. So these are compact, low cost, and ideal for point of care. Is disadvantage that it can do only at a single frequency or narrow band, but its advantage is that a very high sensitive measurement. The third one is an important area, microfluidic, where there are planar sensors like this one, and then it is integrated with tiny fluid channels or microfluidic channels, and here we push in a very small liquid, small kind of fluids into the sensor, and this gives us level-free real-time single cell sensing. Now, if we compare these three broad areas, we will see that the broadband gives you the most complete picture but less accurate, resonant for fast, low cost, and much more accurate and sensitive, and microfluidic for the smallest liquid and single cell samples. Going forward, in next 4 slides, we will take up some case studies. Now, I've taken these case studies from standard literature, and I have marked the paper and the authors below. But irrespective of my choice of this paper, please remember that intellectual property right for these individual works rest with that respective institutes. For example, the first one is IEM Kolkata. The first work, primarily driven by Professor Govindo Sen of IEM, it is about portable microwave sensor for characterization of edible oils. So at the input, you see different kinds of oils, cooking oil, castor oil, mustard oil, etc. Then you see there is a sensor. The sensor essentially is the part C1, which is a double square ring with gap, and it has come through modification of A and B. The idea over here is very simple. Using physics-based knowledge, the inventors or researchers have managed to localize very high electric field in this very small area. And if you see that fabricated sensor, there are two connectors. One side is input, the other side is output, and it is a transmissive type. That means you put a signal over here and take out the signal and put both of them to VNA. First, you put the container which is made of a PLA, measure the response, and then in the sample container you put different kind of oils. The right hand side picture for the first time in this presentation will give you an indication of what I was talking about the frequency response. You see, if you see the figure, on the x-axis there is a frequency in gigahertz, and on the y-axis is the amplitude, transmission coefficient in dB. So it starts with 0 and negative because there is no amplification, So the transmission coefficient at best can be 1, which is 0 dB. Now with frequency for different materials, as it goes, as frequency swept from 2 to 4.5, for everybody there is a particular frequency measure where the transmission coefficient vanishes. That means it dips. For example, without container it dips somewhere between 3 to 3.5, but for the mustard oil, olive oil, and flaxseed oils, which have higher permittivity, those materials load the sensor, and the net effect is that the dipping frequency comes down. They are very close to each other, but you can also see the distinction through human eyes. So, this is a very clean example of a very sensitive portable sensor. Second example is antenna-based permittivity sensor from IEM done by Professor Shah and Sharkar. This is a very interesting work. It is basically an antenna which is meant to diagonally fed square patch, which is meant to radiate in two frequencies, the lower LTE band 700 megahertz and 2100 megahertz. But simultaneously, it can also detect the quality of liquid and quality of solid. How it is done? If you see this patch, the researchers have corrugated the edge of the patch. This corrugation essentially is again enhances the local electric field around the patch edges. So that is used by liquid under test. So you can note that there is a pipe, a transparent pipe that is moving around this patch through which a liquid is pushed. And at the center of this patch, there are slots of a particular dimension. This is where the knowledge, the design knowledge comes in, and where the solid slabs are put. Now, if you see on these two figures, it will be clear. Now, measured resonance sheets for ethanol water mixtures, you see so many different dips. All the dips correspond to one kind of percentage mix between ethanol and water, and this is done in this lower frequency band 2400 to 3100, and there are distinctive frequency response. Looking at the frequency response even through eyes, one can say that these are different. Similarly, on on this frequency type 2125 to 2175, we can see that there are distinct changes between different kinds of, these are all PTFE kind of materials, plastic material used in RF, but they are distinctly different. Next, we move on to another important area. So that is called human body phantom. We were talking about biomedical application. Next two slides, we will be talking about those. So in this work, what the researchers have done, they have assumed two cases, that there is a requirement of implantable antenna. That means there are devices embedded inside body, one connected to heart and one connected to brain, that is deep brain neurosimulator. Now, while these are implanted inside, uh, to communicate that device, to communicate to outside world, we need antennas. Now, to design that, the researchers have used two different kind of models. The top one I am marking over here is a 7-layer brain model, and the bottom one is a well-known heart model, that is skin, muscle, and fat. So while these are multiple layers, when you are trying to cover this with antenna, we need to know the effective permittivity of this layer. That is what is mathematically derived. Now, once you have an equivalent model for this, the workflow goes on like this, that for any multi-layer human body models, you can calculate the effective permittivity, and using that, you can design an antenna embedded in that model. And then you carry on with the standard antenna design method. So Authors have also created liquid phantom and tested, and this is a part of the PhD work of Dr. Soham Ghosh and in Jadavpur University. The last work is from TCS, and this I am also the co-author. This is a microwave-based non-contact edema severity monitoring with machine learning. Now we have come to a situation where when we do the exact measurements, because now if we consider this abnormality is deeply embedded inside body, let's say it is subcutaneous edema. The changes that will be seen from the top will be very small and difficult to decipher through analytical methods. So we use machine learning. On the left-hand side, you see that we consider a standard cylindrical human tissue model of skin, fat, and muscle. These are well known. We bring an antenna in proximity, that is 10 millimeter. When an antenna is brought in proximity to the skin being having high permittivity, the antenna gets detuned. And to do the measurement, we retune the antenna again. Then we conduct the measurement. We take PU foam as a replacement and dig hole, put waters in different quantities like this, and then cover it, and then use that antenna on the top of it with a 10 millimeter spacing and take it through vector network analyzer. In the vector network analyzer, what you see is what this bunch of curves that are seen at this moment. Though all of them are distinct, but if we ask you to say which one is what, it may become very difficult because they are so closely spaced. But this is elegantly done through machine learning. So what needs to be done? First, extract those features which makes sense. Things like resonant frequency, resonant impedance, bandwidth, etc. They are pushed through a, elegant classifier, the details of which is in the paper. And this model is used on test data to get the severity in low, medium, high. And this is done with a remarkable accuracy of 93%. Now, from this case studies, it seems that a lot of work has been done. So today's method may be at a very mature stage, but it is not. Despite this, all these rapid progresses, several fundamental problems recur. Now, remember the point that as we move from 2026 to 2030, we are looking at a situation of ubiquitous sensing and then measurements. So there are multiple challenges. The first challenge is sensitivity versus selectivity. So sensitivity means we need to need a very small concentration of a molecule, addition or deletion. It can show a measurable shift. So if we define sensitivity, it is the ability of the system to detect the weakest possible signal from a target molecule. And it is usually governed by signal to noise ratio. Now, high sensitivity means that we can detect a very low level of concentration. But what is selectivity? It is the ability of the system to unambiguously distinguish a specific molecular species. Microwave spectroscopy is inherently one of the most selective analytical techniques. Now, there is a fundamental trade-off between sensitivity and selectivity. Let me explain very briefly this. For example, consider a radiometric measurement. Radiometers are passive radars which work on detecting an object through blackbody radiation. Now, temperature sensitivity improves with increase in receiver bandwidth. But if you increase the receiver bandwidth, selectivity goes down. Selectivity demands that we build a filter bank of very narrow channel, almost like a hyperspectral imaging. So that is a contradiction. The second challenge is calibration. You noted that all of us have used in this case studies costly VNAs. The VNAs are very, very costly and they need to be recalibrated again and again because what we are trying to do is that we are trying to compensate for the vector error. And not only the cost of the instrument, but the method itself is very costly. Then high frequency metrology, while we can potentially get very small cues from high frequency, but this here high frequency is very brutal because the wavelength is very small, the phase errors are very high, noise is very high, attenuation is also very high. So here another issue is a thin, fragile and non-uniform sample. The final one in the biomedical case is very important. There is a clear clinical translation gap, phantom to in vivo gap. So we have to generalize a method across biological variability and cross section. And if you want to design or develop a machine learning method, you need a standardized number of standardized data sets which are missing. That is an important area to remember. So all these challenges are exactly where data-driven and AI methods add the most value. So how AI answers these challenges? Now AI has become the engine of modern sensing. So we have, let's say we have noisy raw electromagnetic signal. We are trying to convert into fast, reliable, decision-ready insights. So till date, we have been using a closed form models based on our physics, intuition, and logical processes to predict what will happen if this particular parameter changes. From there, it is time for scalable deployment ready instruments. We move into data driven inference methods. Let us see sensitivity versus selectivity. In situations, typical situations where selectivity is described in terms of molecular rotational transitions, we say that selectivity improves by changing the physical environment. That is, you lower the temperature, you increase the pressure and do the measurement. But instead of relying entirely on physical aspects of sensing, let us consider that we use deep neural networks like CNNs or GANs, and can they be trained on known molecular transition profiles? So they can ingest overlapping noise-heavy spectra, and thereby they can separate around very closely spaced intersecting peaks. Second part of it is calibration burden. We want to move into calibration light inferences. So the technique is algorithmic error correction and virtual calibrations. So in a deployment scenario, instead of pausing this operation for physically calibration kits, let us consider that there are machine learning algorithms that can model and predict the systemic drifts, thermal drifts, and based on an assortment of environmental sensors. So what this algorithm will do is that whenever there is a substantial change that is sensed, it will mathematically recalibrate the entire system dynamically on the fly, eliminating the manual overhead. In the case of high frequency metrology, where we have to see hidden cues, there is a potential for a method that is called generative spectral superresolution. Now, we all know of AI architectures like transformers and diffusion models. What they do, they treat these noisy attenuated spectra as low resolution images. And from there, they reconstruct the missing spectral features with using super resolution engines. And the best application is clinical translation gap using multiple learning methods. A number of work is going on in this area. It can generalize across subjects and sessions. So the takeaway is machine learning turns MDS's hardest measurement problems into data-driven inferences, delivering selective calibration-like clinic-ready results. So now we are at the fag end of our presentation. So let us see what are the current frontiers. Where are we heading towards? So now two complementary things are happening in tandem. One part of it is reinvention in the hardware space, and the second part is bringing the intelligence to computation methods. So in the hardware place, the choice I have already talked about, that if you can enhance the electric field concentration, you will increase the sensitivity. So one way to do it, and in low cost, affordable, and a very unique way, is designing of metamaterial resonators. Lot of number of researchers are working in this area to design new kind of designs. These are it won't be possible for me to explain what metamaterial is in this short time, but this is an area in itself, and it is showing lot of promise for in the sensing field. And then simultaneously you push the operating frequency towards millimeter wave and sub-TRML, thereby making the sensing very small in size. So the sensor grows smaller, faster, and more selective. The second important part is computational sensing. Computational imaging was first seen 2 decades earlier. So, in computational sensing, in classical cases, what we have always done, we have taken an industrial gate sensor and we have relied on the sensor to give us a meaningful signal from which we have used classical signal processing to extract the intelligence. But computational sensing puts the onus both on the hardware as well as the computation. These two are designed together. So there are inverse models which supplant the closed form analytical inversions, and sensor and algorithms are co-designed and jointly optimized. So intelligence migrates from the instrument into the algorithm. So finally, I summarize my talk. So as a summary, we talked about the fundamental characterization, non-destructive level-free sensing. Biomedical and IoT are the major areas of investigation. Lot of work is going on in this area, particularly in tissue characterization. The future is for AI augmented sensings, where ML converges into real-time multi-analyte intelligent sensors, and there is also a major push towards engineered dielectrics. So our audience should remember that this is a major area which is driving the future of sensing, these metamaterials, on-demand permittivity reconfigurable antennas. And with this, we open the session. I'm closing. Thank you very much. And with this, we are open to question and answer.
Thank you, Tapaji, for this wonderful session. Anyone having any question, please go ahead. You can post your.
Yeah, Shomendra has asked one question. I have two questions. How the AI model that will be used is trained, and which type of model will be more efficient? The hardware software code is, and how can be taken forward for this for the optimum solution? The second part I will ask first. This kind of solutions have been shown to work well by Mitsubishi Electric Lab. If you go to the website MERL, they will explain how this software code design has been done. So now, a very simple example, consider what we do. Let's say we want to do a tomography of a human body or any object. We put number of antennas, let's say 12 or 14 antennas around us, and we define different configurations and try to mathematically model those configurations. That one is transmitting, rest of them is receiving. But to make these systems very accurate, we need number of probes, isn't it? So instead of that, we in the software computational part, let us assume that we have some prior knowledge. It is called a deep prior. We have some small amount of data with which we have trained an initial model. That initial model rests on these antenna-based systems, and we can now use reduced number of probes to see whether we get this inference that we desire. So that is what is computational sensing. Another example is computational imaging, in which the lens, what is done is the Fourier once you capture that image, you convert into frequency domain, you do a Fourier transform, and that is very costly. So there is a scheme of 4 lenses in which what you get on the receiver is basically the image itself is a Fourier transform of the original image. That reduces the computational effort. So that is how this design happens. Now, how this AI model will be used is trained. So what researchers are doing is that, for example, what TCS research is doing is that they are developing their own sensing systems. Either they are using commercial off-the-shelf sensors, and where it fails, people are designing their own sensors. Like in IEM, people have done that, and using those sensors with number of analytes, they are collecting a lot of data. The data is getting annotated, and initially all those known machine learning models like random forest, SVM, and others, they are used to see whether accuracy is received or not. And that is how, once you try with a different type of models, we'll come to know which one is more efficient. But that doesn't mean that it will be deployable across industry. For that, we have to generalize it, and that is where a lot of research needs to be done. Any other question?
Yes, I think we have a question from Jay.
I'm not sure. Where is it, in the chat or?
In the Teams chat. Okay.
Yeah, yeah.
Yes,
So
there is a
my question is, apart from technology, is any other technology is used to capture this application? What means? Yes, means this is one part of the technology. Microwave spectroscopy is not the end all. For example, let's say food, perishable foods. We do not, microwave spectroscopy is also little used in these cases. This is a very new concept. So the most common examples where common type of sensing that people have used where microwave is used are the first people start with vision. Okay. So once and vision fails if you try to see beyond an obstruction. That is where people have naturally considered microwave or radio. And then also for these food cases, you can use what is known as design E-nose. Right. So if it is the food is or fruit is degrading, it exhales a particular chemical which can be picked up. For example, there is a lot of work going on in Jadavpur University where they have developed a number of very good quality electronic noses uh, to classify Darjeeling tea, whether they are good or not. So there are different kind of technologies. All of them have their own limitations and challenges. So microwave has a particular kind of advantages that it can see through the barrier from a distance. And also for biomedical, it is safe for human beings. Supposing you have to see, it is a futuristic. Supposing you have to see to understand brain atrophy. Isn't it good if microwave in future can be used to see your conditions? Okay, there are questions from Jatin. How do you ensure that AI models will remain accurate when applied to answers? No, I cannot specifically uh, claim that I'll be ensuring that it is always accurate. This is not possible. Only thing is that there are very well-known standard methods in which the data has to be annotated, and then you do select a portion of the data for training and testing, and essentially look into the noise aspects, balancing aspects, and then do. So the more data you capture of various kinds of stages, the better you ensure the accuracy and also ensure the generalizability. Another question is from Gaurav. How a biological material's response to an electrode differs from and matches an engineer significantly it differs because the biological material, if you look at it, I mean, if it is not a single layer material. First of all, biological tissue is a composite material. It has multiple layers of it. If we, the very simplistic model will have, say, for example, skin, it will have fat and muscle. But the most important factor of it is the one is the content of water, and second part of it is the loss tangent, and that loss is much higher as compared to an engineer materials response. So, and it is quite difficult to build a biological material in laboratory. Keeping it can be created, but created for a short time before it collapses. How close are we to achieving fully automated material characterization system? Now we are not very close. There are a lot of groups, lot of companies are also trying this out, material color characterization, but these are very specific applications. For example, in India right now, a lot of groups are trying out detecting defects in composite materials. You have composite materials or slabs used in many production scenarios. So first it has to be understood very well. For example, in some cases, let's say a kind of work I have seen where you have to detect the paint quality without touching. The sheet on which the paint is wrapped, that sheet is moving at a very high speed. So fundamentally, the sensing system or the detection system has to first get integrated with the manufacturing process unless you are developing the system from as a greenfield operation. So, but the efforts are going on. Those legacy companies are slowly continuing to do pilots operation, and in limited scale, these have been found useful.
I think, Tapasji, I believe you have answered all of the questions
Mhm.
and very well ahead time as well. I think the knowledge that you have shared, that's a really good for us to understand what about the spectroscopy part. I would like to thank you so much to share this knowledge to our team.
Thank you all. Thank you, Umeji, and thank you, Saraca, and thank you all my audiences. It's my pleasure. Hopefully, we will meet again.
Sure,
Thank you.
Tapasji. Yeah, good to wrap up.